Okay, so let's talk nuclear chemistry. So this is going to be chemistry that happens in the nucleus of an atom. And so instead of talking about electrons and polarity and those kinds of things that we've been talking about in electrochemistry, now we're going to talk about protons and neutrons that are in the nucleus of all of our atoms. So it's going to be different. We're going to learn a different way to balance equations. It's super easy, so don't worry about it. But we're going to learn a different way to balance those equations. Then we're going to talk about how do we know what types of reactions these are going to do, which direction they go, and we're going to come back to a little bit more of the rate stuff that we did earlier on and talk about how fast these reactions go and what kinds of calculations we can do for that. All right. So first things first, since we're talking about nucleus reactions and nuclear reactions, we need to have a way to talk about where those particles, the protons and the neutrons, are in our atoms and what they look like. And to do that, we use something called standard representation. All right, so standard representation is going to be, you're going to have your element. We're going to use element X, right? And we're going to have down here, we're going to have the charge of element of the nucleus, right? Charge of the nucleus. Now, of course, the only charged particles in the nucleus are protons, so this is also the number of protons, which corresponds to the atomic number. So we got three different things that are happening in this Z number, right? This is the number of protons, it's the atomic number, and it's also the charge of the nucleus. And then at the top here we have, this is the mass of the nucleus, and this is the number of protons plus the number of neutrons. And so, and this is the atomic mass of whatever element we're talking about. Atomic mass. So we have two pieces of information. Well, three, I guess. We have the element that we're talking about, we have the atomic number of that element, and we have the atomic mass. Now, the atomic mass will change depending on how many neutrons we have. And so when we change, right, so when the number of neutrons changes, uh, that means that we're making a new isotope. We create, oops, a new isotope. So if X and Z are the same across uh, two elements, but the A number is different, the mass is different, that's a different isotope. Okay, so we can do standard things. We can do the easiest ones are things like hydrogen, right? Hydrogen is a single proton in the nucleus and there are no neutrons. So hydrogen has one proton and a mass of one. So one proton, one proton. This is how we represent your standard hydrogen atom. If we go up from there, helium is going to have two protons in the nucleus and two neutrons. And so we have two for our atomic number, helium, and four is the atomic mass. With two neutrons plus two protons gives a mass of four. Now, this number, this bottom number, will always correspond to the elemental symbol. Every time we have a 1 down here, the elemental symbol will be hydrogen. Every time we have a 2, this will be helium. Every time we have a 3, lithium, 4, beryllium, on and on, right? Um, so what this tells us is that we have, right, so these two things are going to be related. Okay, so these two are always going to be related, right? See periodic table. Right? Anytime we have a 1, it'll be hydrogen, et cetera, et cetera. Um, and then, of course, the other number, the number that's not in this circle here, that's where we look at the isotopes, the different isotopes of hydrogen. So if we have a 1 here, that's one isotope of hydrogen. This is hydrogen 1, right? This is helium 4. But we can also have things like helium 3 or helium 5, et cetera, right? So those would be different isotopes. This number up here is the one that we put there. There are other particles that we are going to use, and these particles are not in the periodic table. And so we're just going to list those really quick here, and we'll come back to them definitely in the future. So one of those particles is an electron, right? So an electron has no mass and a negative charge. And so how would we represent that here? We're going to use a small e for our symbol. We're going to have a charge of -1 and a mass of 0. Right? So an electron looks like this, a charge of -1, a mass of 0. We can have just a neutron, right? If we have just a neutron without anything else in there, what we're going to have is no charge, because neutrons are, of course, neutral, N for neutron, but the neutron has a mass of 1. So if we have just a neutron with no protons around, we'll have a charge of 0 and a mass of 1. Just an electron, charge of -1 and a mass of 0. We don't have a symbol for protons because if you just have a proton, that's a hydrogen nucleus. And so then we have a mass of 1 and a charge of +1, and you have hydrogen, right? So notice that neither of these have a +1 is their charge because, right. Now, there is one more that kind of breaks all these rules, so I've saved it for last, and that is the positron. The positron is the opposite of the electron. You have the opposite charge, but you still have no mass. And so a positron is a +1 charge with no mass. And so it's not a proton, so it's not a hydrogen nucleus. So this is kind of the exception to the rule. When you have a +1 down here, when I said all was related, like 2 minutes ago, it turns out the always was maybe an overstatement because here we have a 1 that's associated with a positron as opposed to the hydrogen nucleus. So these three other particles, the electron, the neutron, and the positron, we will also use occasionally in our nuclear chemistry reactions. So that's standard representation. These are the particles we're going to use. Most of them come from the periodic table, except for the three exceptions that I listed, the electron, the positron, and the neutron.